Hi, it's Megan over at the Math Workshop. I just finished reading chapter one of this fantastic book, Figuring Out Fluency in Mathematics, Moving Beyond Basic Facts and Memorization. I know a lot of math teachers have been devouring this book lately. What about you? Have you had the opportunity to read it? If so, what did you think? I'm going to share some of my takeaways just from chapter one of the book in this video. First off, I was very excited to dig into the understanding of procedural fluency because as a math coach, I've spent a lot of my learning exploring the conceptual understandings of math operations, concepts, and big ideas. So this book was needed by me. In this video, I'm really going to share my thoughts and my takeaways, as I mentioned. So let's dig in. The authors opened up chapter one by sharing this definition of fluency from NRC and NCTM. Fluency, being able to apply procedures efficiently, flexibly, and accurately. Let's take a deeper dive into those three words used to describe fluency that the authors shared. Efficiency, solving a procedure in a reasonable amount of time by selecting an appropriate strategy and readily implementing that strategy. Okay, we're not talking time test here. That's not what we're talking about. We're talking about in a reasonable amount of time. And we'll talk in a moment about what might be unreasonable. Flexibility, knowing multiple procedures and applying or adapting strategies to solve procedural problems. So I think of that as being flexible, not me trying to be flexible in yoga class, which I do try to do, but being flexible in that, okay, here's the problem that I have to solve. Okay, what are those strategies that are available to me, and which one should I choose for this particular problem? Like, which one's the best for this problem? Accuracy, correctly solving a procedure. Okay, this is math class. We do want to correctly solve the problem. Efficiency, flexibility, accuracy. This phrase gets thrown around a lot in math world. Appropriate strategy. I really liked how the authors describe their definition of appropriate strategy. Of the available strategies, the one the student opts to use gets to a solution in about as many steps and or about as much time as other appropriate options. So there might be many appropriate strategies. In the book, in chapter one on page 12, the authors share this activity 1.3. It's called, Is It Reasonable Routine? I love this, and I'm thinking about making a slide deck to go along with this to use with students I work with. They shared that you can teach students a sign language, which is on the slide, sorry, I love this, for reasonable, and for unreasonable. So that's that quiet communication way, nonverbal communication way that once you pose the question, students can quickly respond. I love this. I could see having these two graphics up. I plan on doing this with students this fall. So look at the examples that are on the slide for these reasonability statements. And students are asked to think about, is it reasonable or not? So 985 take away 328 is about 600. Is it reasonable or not? 2 and 56 hundredths times 4 is about 10. Is it reasonable or not? 24 and 27 is about 50. Is it reasonable or not? 17/30 is about 60%. Is it reasonable or not? I love this. I could see that students would have that gift of silence, that think time to really think their own thoughts about these statements. And then they could share their thinking with a shoulder partner or an elbow buddy or a small table group. In the book on page 14, the authors share an activity called 1.4, activity 1.4, called Is it a good choice or not? They actually call it, is it a good choice or a bad choice? But I think when I modify this to use with students this school year, I'm going to say, is it a good choice or not? That just works for me. What they recommend is posing a problem along with a strategy explanation and giving students that think time to decide if the strategy is a good choice or not. First, having students explain what the student did, and second, having students tell if they think that strategy was a good choice or not and why. Third, asking students to offer alternatives for the problem where they decided the example wasn't a good choice. I really like this activity as well as the previous one because it offers students the opportunity to discuss efficiency with each other, which I think requires quite sophisticated thinking and reasoning. So let's look at this example, 37 plus 74. So the strategy that they used was they counted up by ones from 37 to 74. So is that a good choice or not? 4,260 divided by 60. And this is what the student did. They broke 4,260 apart into 4,200 and into 60. And they divided both parts by 60 and then added them back together to get the answer. Is that a good choice or not? And why? I love this. I plan on using this in the fall as well. What do you think about this idea? I loved a few pages later in chapter 1, the authors wrote these beliefs. So, productive beliefs about procedural fluency. Oh, I love these so much. These were on page 18. Which ones resonate most with you? So, number one, procedural fluency is an attainable goal for each and every student, not just some students, each and every student. Each student is capable of developing a repertoire of strategies and learning skills at applying those strategies flexibly, efficiently, and accurately. Number two, procedural fluency is a function of opportunity, experience, and effort. Differentiated supports enable that each and every student can understand and use a wide range of strategies. Number three, procedural fluency instruction is higher order thinking as students create strategies, generalize when to use a strategy, and explain why a strategy works. This increased level of thinking leads to greater understanding and performance for every student. Number four, every student must have access to instruction and resources that attend to all procedural fluency components and actions. Number five, having a range of ideas and strategies for solving procedures enriches everyone's learning. Therefore, every student benefits from heterogeneous grouping. Conversely, homogeneous grouping, ability grouping, is detrimental to developing procedural fluency. I'm curious, which of those five resonated most with you? I really like the second one, as it reminds me of the importance of growth mindset. I love the work of Dr. Carol Dweck and Dr. Joe Bowler. That really resonated with me. I also really like the last statement. as it makes me reflect on the growth that I have seen in my students when they were given the opportunity to work in heterogeneous groups. So 2 and 5 really resonated the most with me. Feel free in the comments to let me know what resonated most with you. Well, let's pause from the book for a moment and let's play a little game. This game's called How Well Do You Know Your Standards? And is it referring to the standard algorithm? So this book that I'm reading is making me think about procedures and strategies and standard algorithms. And I reflect on one of the jobs that I've had as an educational consultant, coaching in math classrooms across the United States. And a large part of my work was helping educators interpret and understand their state math standards. So let's pause for this quiz for a moment, and I want you to think about how well do you know your math standards. Now, I'm going to go ahead and pull from the Common Core math standards for this opportunity right here. But honestly, in my experience of traveling the country and working with many, many, many different states and unpacking their standards, they're mostly all the same. They're mostly all very, very, very similar to Common Core, maybe with some little slight tweaks. So I think it's okay if we use Common Core for this experience. All right, here's your first standard. Fluently add and subtract within 100 using strategies based on place value, properties of operations, and or the relationship between addition and subtraction. First, I want you to think, what grade is that from? And second, I want you to think, is that the standard algorithm? Is that what that language is talking about? You ready for the answer? That is grade 2. That is not the standard algorithm. All right, you ready for the next one? Add up to 4 two-digit numbers using strategies based on place value and properties of operations. All right, you remember those? Commutative property, do you remember? What grade do you think that is? And is that the standard algorithm? You ready? That is grade 2 as well. And no, that is not the standard algorithm. That's about strategies based on place value and those properties of operations. Let's keep going. How are you doing so far? All right, here's a big one. Add and subtract within 1,000 using concrete models or drawings and strategies based on place value, properties of operations, and or the relationship between addition and subtraction, that inverse relationship. Relate the strategy to a written method. Understand that in adding or subtracting 3-digit numbers, one adds or subtracts hundreds and hundreds, tens and tens, ones and ones. Sometimes it is necessary to compose or decompose tens or hundreds. What grade is that? And is that the standard algorithm? You ready? We're still in grade 2. Did you know that? And that is not the standard algorithm. All right, you ready for the next one? Fluently add and subtract within 1,000 using strategies and algorithms based on place value, properties of operations, and or the relationship between addition and subtraction. So if you're keeping track here, that's the first time we heard the word algorithm. What grade is that? And is that the standard algorithm? That is grade 3. That is not the standard addition algorithm or subtraction algorithm. It's not. How are you doing? You ready to keep going? All right. Oh, first one for multiplication. Multiply 1-digit whole numbers by multiples of 10 in the range of 10 to 90. So for an example, 9 times 80, 5 times 60, using strategies based on place value and properties of operations. We're hearing a lot of the same phrases over and over, aren't we? What grade is it? Is that the standard algorithm? Third grade? That is not the standard algorithm. Here we go. Fluently add and subtract within 1,000 using strategies and algorithms. Just heard that word again. Second time now. Algorithms based on place value, properties of operations, and or the relationship between addition and subtraction. What grade? Is that the standard algorithm? If you're keeping track, we haven't seen it yet. That is third grade. That is not the standard algorithm. Let's keep going. Here we go. Fluently add and subtract multi-digit whole numbers using the standard algorithm. Ding, 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 ding. We just heard it. Here we go. What grade is this? What grade? Grade 4. Grade 4 is the first time standard algorithm shows up in the Common Core math standards. That is the standard algorithm for addition and subtraction. All right, we still have more. Multiply a whole number of up to 4 digits by a 1-digit whole number and multiply two 2-digit numbers using strategies based on place value and the properties of operations. Illustrate and explain the calculation by using equations, rectangular arrays, and or area models. What grade is that? And is that the standard algorithm? Grade 4? No, that is not the standard algorithm. Next up, find whole number quotients and remainders. Ooh, our first one on division. With up to 4-digit dividends and 1-digit divisors using strategies based on place value, the properties of operations, and or the relationship, not between addition and subtraction. Now we're moving on to the relationship between multiplication and division. Illustrate and explain the calculation by using equations, rectangular arrays, and or area models. We just heard that language in the last one for multiplication. What grade is this? And is this the standard algorithm? Fourth grade. No, it is not. Fluently multiply multi-digit whole numbers using the standard algorithm. Ding, ding, ding. If you're keeping track, there's our second time we've heard standard algorithm. What grade do you think this is? Multiplication standard algorithm. Did you guess grade 5? That's the standard algorithm. Okay, if you're keeping track, we've done standard algorithm for addition, subtraction. Those were in 4th grade. Multiplication was in 5th grade. We have one more operation left that we haven't explored where the standard algorithm is. You ready? Find whole number quotients. There's that operation of division of whole numbers with up to 4-digit dividends and 2-digit divisors using strategies based on place value and the properties of operations and or the relationship between multiplication and division. Illustrate and explain the calculation. Here's that same language we've been hearing by using equations, rectangular arrays, and or area models. What grade? And is that the standard algorithm? 5th grade? No, it is not. All right, we're getting near the end now. Add, subtract, multiply, and divide decimals. All right, we just left whole numbers. We're moving into decimals to hundredths using concrete models or drawings and strategies based on place value, properties of operations, and or the relationship between addition and subtraction, relate the strategy to a written method, and explain the reasoning used. What grade is that? Operating with decimals? And is that the standard algorithm? Grade 5? And no, it is not. All right, I think we have one more slide. Here we go. Fluently divide multi-digit numbers using the standard algorithm. Ding, ding, ding. We just got there. Long division. What grade is this? Grade 6. Yes, that's the standard algorithm. How did you do? Oh, I had one more. I lied. Forgot. Fluently add, subtract, multiply, and divide. It was the decimal ones I forgot. Multi-digit decimals using the standard algorithm for each operation. What grade is that? Did you guess 6th grade? And yes, that's the standard algorithm. So to conclude, these are the standard algorithms. Probably for you and I know for myself, I can speak for myself, this is how I learned in elementary mathematics when I was a student many, many years ago. Carrying, borrowing, don't think we use the word trading, but all these steps that I usually messed up and forgot, especially in long division, because I did not have that conceptual understanding. I didn't understand why we were doing it. I just tried to memorize it and tried to keep up. So now standards are written so that students have a depth of conceptual understanding so that when they eventually and finally get to the standard algorithm that mathematicians did come up with and decided, hey, this is a great way to work in this operation, then they're more likely to remember what they're doing, understand why they're doing it, and how it works. Whew, I wish I would have learned that way. So to summarize, it's never too late. To summarize, a standard algorithm for addition and subtraction. Do you remember what grade that is for most states, most places is required for students? Grade 4. How about the standard algorithm for multiplication? For most places, where do you think that shows up in the standards? Grade 5. How about the standard algorithm for division? That long division shows up in grade 6. I understand and have a lot of empathy in coaching teachers. This is confusing, and I think there's two main reasons why this is confusing. One, we learned these algorithms, these standard algorithms, at much earlier ages than what is recommended in the standards today. I think it's a good recommendation. I do, as you have heard me say. I believe students need to build that conceptual understanding so that they know why they're doing what they're doing, how, why it's working, what the underlying concept is beneath it. I also think the second reason why this is very confusing for teachers, and I wholeheartedly understand, is most of the curriculum that I've seen across our country, different textbooks, different programs, different materials introduce the standard algorithms a lot earlier than they are supposed to. So they're not in alignment with these standards. And maybe a third reason, honestly, could be, and I understand this too, parents like myself, I'm a parent, I was taught in a different way. I was just taught the standard algorithm. I certainly, when I was a child, did not know what adding by place value was. I didn't think about decomposing numbers. I had no clue what the distributive property was. I think I heard about it in middle school, but I did not know what it was until I became a teacher and really started understanding, oh my goodness, if I don't know 7 times 7, I could use the distributive property and figure out 3 times 7 and 4 times 7 and add those products together and get 49. So parents, I think, sometimes share too early, or maybe older brothers and sisters, or tutors, or different people in children's lives. So carry on what you're doing, and thank you for joining my sharing of figuring out fluency in mathematics. With a little sidebar of the last couple slides was just a little bit of education for you. And I hope that you have enjoyed this video and look for the remaining chapters of this amazing book. Thank you to the authors who wrote this fantastic work. I know I can't wait to work with students in fall and use many of the ideas that they've shared. And if no one has told you today, thank you for what you're doing. It makes a difference, and we appreciate you.